All right, question 64. This question, nothing too hard is going on here, but just kind of parsing what it's telling you and what it's asking you can be a bit of a challenge. So let me go through this a little bit more carefully. F and g are these continuously differentiable real valued functions. F of 0 equals 0, g of 0 equals 0, and g prime of 0 does not equal 0. And the question is, can we necessarily extend the function that's a quotient of these two functions to be a continuous function? At least that's the question in part A, and the answer is absolutely you can. Maybe think f of x is equal to, I don't know, it really doesn't matter, maybe sine of x. And g of x is equal to, let's say, x squared minus 4x. Sure, that'll work. Note that f of 0 is equal to 0 because the sine of 0 equals 0, and g of 0 is equal to 0 because 0 squared minus 4 times 0 is 0. If g of x is x squared minus 4x, it's easy enough to figure out g prime of x. That would be 2x minus 4. And now we can verify that g prime of 0 does not equal 0 because g prime of 0 is 0 minus 4. In other words, negative 4. These two functions for f of x and g of x satisfy the requirements in this problem. If these functions represented f of x and g of x, let's see if we could extend the quotient of these functions to a continuous function in a neighborhood of 0. And if we can do so, that example might help us prove that we can do this more generally for any f in g. So if f of x is sine of x and g of x is x squared minus 4x, f divided by g would just be sine of x divided by x squared minus 4x. This function is not defined when x equals 0 because we'd have to divide by 0. So what we want to do is consider the limit as x approaches 0 of this expression. You might notice that this quotient is this 0 over 0 indeterminate form, and therefore we can apply L'Hopital's rule to evaluate this limit. We get that this limit is equal to the limit as x approaches 0 of the derivative of sine of x, which is cosine of x, divided by the derivative of x squared minus 4x, which is 2x minus 4. This expression is continuous at 0, so I can evaluate this limit by just changing all of the x's into zeros. I get 1 divided by negative 4, in other words, negative 1/4. Because the limit as x approaches 0 of this quotient is negative 1/4, what I can do is define this function h of x to be equal to sine of x over x squared minus 4x if x does not equal 0, and negative 1/4 if x does equal 0. This piecewise function would be continuous in a neighborhood of 0. I've satisfied the criteria. I've extended this function to be continuous in a neighborhood of 0. Worth pointing out that this function is not continuous at 4, but that's not relevant to this problem. Yeah, okay, great. You did this for one specific value of f and one specific value of g. But in order for statement 1 to be true, you have to be able to do this for any function f and g satisfying the given criteria. Well, no problem. I can just redo this more generally. We'll leave f of x as f of x and g of x as g of x, and we'll consider the limit as x approaches 0 of some arbitrary function f of x divided by some other arbitrary function g of x. Because f of 0 equals 0 and g of 0 equals 0, this is the 0 over 0 indeterminate form, so we can apply L'Hopital's rule. L'Hopital's rule tells us that this limit is equal to the limit as x approaches 0 of f prime of x divided by g prime of x. Note that because g prime of 0 does not equal 0, we know that this thing exists. We can let c represent whatever number this is. What I'll now do is define this function h. I'll let h of x be f of x divided by g of x, as long as x does not equal 0. But if x does equal 0, I'll define this function to be equal to this constant c. As long as f of 0 and g of 0 equals 0, I can apply L'Hopital's rule. As long as g prime of 0 does not equal 0, this limit is equal to some constant. I can use that constant to extend this function to be continuous in a neighborhood of 0. Statement 1 is true. Statement 2 looks a lot harder, but it'll end up being kind of the same. You could go through with a specific example and show how it works if you want, but hopefully this example illustrated this general case well enough that I can just use this general case to prove statement 2. The function that I'm interested in extending is no longer f divided by g. It's now f squared minus f divided by 2g minus g cubed. All right, fine. I want to extend this thing to be continuous in a neighborhood of 0. What that means is I need to know what the limit as x approaches 0 of this expression is equal to. Well, it'd be great if I could use L'Hopital's rule, but be careful, you can only use L'Hopital's rule if this is an indeterminate form. Fortunately, we know that f of 0 equals 0, so f squared is 0, and 0 minus 0 is 0. And g of 0 equals 0, so 2 times 0 is 0, and 0 cubed is 0, and 0 minus 0 is 0. This is again that 0 over 0 indeterminate form. So I can use L'Hopital's rule, and instead of evaluating this limit, evaluate the limit as x approaches 0 of the derivative of the top, which if I use the chain rule, I first take the derivative of the squared part to get 2f, but then I'm not done. I have to multiply by the derivative of the inside function, so that gives me this extra f prime. Then from that, I want to subtract the derivative of this f, which is f prime. Down on the bottom, it's kind of the same. The derivative of 2g is 2g prime. And using the chain rule, the derivative of g cubed is 3g squared g prime. Does this limit exist? It would be awesome if it did, because if it did, I could kind of copy what I did up here. Well, we know that f of 0 equals 0 and g of 0 equals 0. So this right here is 0, and 0 times anything is 0. So up on the top, I have negative f prime. And down on the bottom, this g is 0, 0 squared is 0, and 0 times anything is 0. So down on the bottom, I'm left with just 2g prime. Because g prime does not equal 0, this is defined. It's just equal to some constant. Maybe I call that constant c. Now what I can do is define a function h of x to be equal to this messy expression f squared minus f over 2g minus g cubed if x does not equal 0, and c if x does equal 0. By construction, this function, which is an extension of this function in a neighborhood of 0, is continuous. Statement 2 is also true. Are we done with the problem? Unfortunately, no. Right, the answer is either C or E at this point. We've ruled out A, B, and D. But to answer the question, we need to evaluate the validity of statement 3. The function f divided by g can be extended to a differentiable function in a neighborhood of 0. Well, this will end up being false. To show this is false, all I have to do is find a function f and another function g that cannot be extended to a differentiable function in a neighborhood of 0. So the trick will be picking functions f and g so that when I divide these two functions, what I'm left with is something whose derivative is undefined when x equals 0. The example that came to mind for me, although I'm sure there's many others, is to let f of x be equal to x to the 4/3 power, and g of x be equal to x. Note that f divided by g would be x to the 1/3 power, so f divided by g prime would be 1/3 x to the negative 2/3. In other words, 1 divided by 3 times the cubed root of x squared. Let's first make sure that we satisfy all the criteria in the problem. If f of x is x to the 4/3 power, f of 0 is 0 to the 4/3 power, which is equal to 0. That's good news. If g of x is x, g of 0 is equal to 0. That's good news as well. The other criteria that we need to satisfy is to make sure that g prime of 0 does not equal 0. Well, g prime of x is the derivative of x, which is just 1. So g prime of 0 would be equal to 1, which is not equal to 0. Great. X to the 4/3 and x are continuously differentiable real-valued functions on R, such that f of 0 equals 0, g of 0 equals 0, and g prime of 0 does not equal 0. However, as we've shown here, the derivative of their quotient is undefined at 0. Change all the x's into zeros, you get 1 over 0. That's bad. So I can go through the same steps I did before, I guess up here in blue, where I first considered the limit as x approached 0 of x to the 4/3 divided by x. You could use L'Hopital's rule, but you really don't need to. You can just simplify this to x to the 1/3 power. Evaluating this limit is easy. It's 0 to the 1/3, which is just 0. So if I'm extending this function to be continuous in a neighborhood of 0, the way I would do it would be exactly what I did up here. H of x is x to the 4/3 divided by x if x does not equal 0. But since this is undefined when x equals 0, I need a different expression for this when x does equal 0. I'll set this equal to some constant. The constant I'll want to set it equal to is 0, this 0 right here. I now have a continuous function. That's great, but the problem will come when I look at the derivative of this function h. The derivative would come from this expression. This expression is undefined when x equals 0. Therefore, I can't extend this function to a differentiable function in a neighborhood of 0. Continuous, no problem. Differentiable, not always able to do it. Answer to this question is C, 1 and 2 only.